Boyle's law. We're going to study a series of what are called gas laws, and they're named after the scientists who discovered them. So Boyle's law relates pressure and volume. I use their names. I think it's good to honor these pioneering scientists, but I will not quiz you on what is Boyle's law. I want you to know the law, but I have a hard time remembering. There's like 4 or 5 different laws, and I can't seem to remember which belongs to which person. And so I don't think that's an important piece of information to store in your brain. But anyway, so we're going to look at the relationship between the pressure of a gas and the volume of a gas. The pressure depends partly on the volume, or vice versa. So what Boyle's law observes is that if we keep the temperature of the gas constant and the amount of gas constant, then the pressure of the gas increases if we decrease the volume and decreases if we increase the volume. The nice thing about gases, even though we can't see them, and so in that way they're a little difficult to think about, we all have experiences with balloons. What is a balloon? It's a latex container full of gas. So if you think about a balloon, so you've got this balloon and it's filled up and it's tied. So the amount of gas inside is constant. It's in the room. We're not heating it up or cooling it down. If you were able to squeeze the gas and make it smaller, squeeze the balloon in and make it smaller, what would that do to the pressure of the gas inside? It would increase it, right? And if we stretched the balloon, or if we somehow made the pressure larger, I think we all understand that the balloon would expand, right? And so by thinking about balloons, we can understand these relationships between the properties of gases. This relationship between pressure and volume allows things like bicycle pumps to work. So on a bike pump, down here at the bottom, there's a one-way valve that allows air to come in but not go out. And then we've got the part that you hook up to your bike. So when you pull the handle up, it moves a little piston in here. It's almost like a giant syringe. It moves this piston up, increasing the volume inside. That causes a decrease in pressure, and it causes air to come in. On the downstroke, when you push down, you are increasing the pressure by decreasing the volume. The air cannot go out that little one-way valve, and so it's forced into the bicycle tire. So a bicycle pump works on this pressure-volume relationship of Boyle's law. Robert Boyle lived in the 1600s. It was a long time ago. He studied this relationship, and when we talk about the relationship between volume and pressure, we have to think in terms of a constant temperature and constant number of gas particles, constant amount of gas. Because if you change the amount of the gas, if you put more in or take some out, that's going to change things. So one way to state Boyle's law is that the volume and the pressure are inversely proportional. So this kind of funny little alpha sign means proportional to. It's different than equals. So if the volume goes up, the pressure goes down. It's an opposite relationship, an inverse relationship. One gets bigger, the other gets smaller. This is the sort of experiment that he did to study this. He used a J tube that was closed on one end, and so he had a gas sample in there, and then he had liquid mercury in this tube, and the other end was open to the atmosphere. Now, we talked about the Mercury Barometer on Tuesday. And so here we have this sealed off gas. The difference in pressure between the gas inside and the atmosphere on the outside is equal to the difference in the heights of the mercury columns. If the pressure of this gas was the same as the atmospheric pressure, the level of mercury would be the same on both sides. That's what would happen if both ends of the tube were open. Does that make sense? Think about water in a plastic tube, and you make a U shape out of the tube. Is one side of the tube higher with water than the other? No, because the gravity pulls on the water and it comes down the same on both sides. So what this is showing here is that because the gas is pushing down on the mercury, the pressure of this gas is greater than the atmospheric pressure because it's pushing the mercury down. And so it has to come up on the other side. And so we can measure the pressure just with a ruler, measuring the difference in heights of columns of mercury. Because this is back in the 1600s, right? They didn't have electricity. They didn't know what electrons were. Things were pretty primitive in terms of science, and yet they were able to do some pretty amazing things. So he could measure the volume of the gas and the pressure. Now, to add pressure to the gas, he would just pour some more mercury in here. Most of these scientists did not have average lifespans because they played with dangerous things, right? He's playing with liquid mercury. Mercury poisoning is not good for you, right? And they didn't know that, so some of these guys died, unfortunately, young. But by adding more mercury, that squeezes the gas. See how the volume is smaller here? Because you put more mercury in and it pushes on the gas. Gases are compressible. It gets smaller. Now look at the difference in the heights of the column of mercury now. It's much larger. That tells us that the pressure on this gas sample is larger. And so he would adjust the pressure and measure the volume, and then he could graph it. So at low pressure, the volume was high, and as the pressure increased, the volume decreased. And that's how he arrived at the law that is now named after him, Boyle's law. Any questions about that? We can explain Boyle's law using kinetic molecular theory. So here we have a container with a movable top, and it's got a weight sitting on it. And here we've got a more modern pressure gauge. So here we have a volume of 1 liter, and this is a pressure of 1 atmosphere. If we put a heavier weight on this and squeeze the top down, what we observe is that the pressure goes up. If we cut the volume in half, the pressure doubles. So what are these gas particles doing? These gas particles are running into the walls of the container, which causes pressure. If you cut the volume in half, but the gas particles, the number of them is the same, and the temperature is the same, they're moving at the same velocity, they're going to run into the walls more often, right? Because it's a smaller container. Running into the walls more frequently means more pressure. So you reduce the volume, it increases the pressure. Does that make sense? So this is what I think is the most useful way to express Boyle's law. Pressure 1 times volume 1 equals pressure 2 times volume 2. And I'm going to give you these gas laws on exam 4, because it's not on the next exam. Or are we coming up on exam? Yeah, that's right. Yeah, okay. Just a little brain fart there. So I'll give you the actual equations, but you need to know how to use them. So let's look at that. So there's going to be a lot of word problems in this chapter. I'm sorry if you don't like word problems. Always read the whole question. A cylinder equipped with a movable piston has an applied pressure of 3 atmospheres and a volume of 5 liters. What is the pressure of the cylinder if the volume is decreased to 2 liters? Okay, so we read through that. There's some numbers in there. What we're going to do with these types of problems is we're going to make a table, and we're going to bring the numbers into the table so that they're all labeled. So we've got pressure here. The units tell you what this measures, and the words also often tell you. So pressure and volume. So I'm going to make a table. That was a little too big. And so we're going to have pressure and volume. And always write the units in your table. So I'm just going to read through the question again and stop at the numbers. Cylinder equipped with movable pistons applied pressure of 3 atmospheres. Okay, so I want to write that in the pressure column. And a volume of 5 liters. That pressure and that volume go together. So the pressure of 3 atmospheres, the volume of 5 liters. I'm going to just label the first row 1 and the second row 2. Very creative, huh? What is the pressure? That's the question. If the volume is decreased to 2 liters. So something is changing now. It was at 3 atmospheres and 5 liters, and now it's going to change. So that was condition 1, and now this is condition 2, 2 liters. And we have this empty box. That's the question, what's the pressure? So we're going to label that box P2. This is P1, this is P2, V1 and V2. So you put it in a box like that, a table, and then it's much easier to keep track of what's what. Any questions about how I did that? I know story problems, word problems are really intimidating to a lot of students. P1, V1 equals P2, V2. Always makes me want to say R2D2, C3PO. My kids used to call him CP3O. Repetitively, I could not get them to say it right. They figured it out now, but CP3O, what? Okay. So here's our equation, and we are solving for P2. So I'm going to make P2 just a little different. Does that look a little different? A little bit. So I need to rearrange the equation and get P2 by itself. Sometimes students want to put the numbers in first and then rearrange. I really, really don't recommend that. I let students do that one semester and it was a disaster. Don't do that. So this is where some simple algebra comes in. If I want to get P2 by itself, I need to get rid of the other variables that are with it. And I'm going to do that by doing the opposite. So P2 times V2, I'm going to divide by V2. What is V2 over V2? 1. Multiplying by 1 doesn't change anything. So I can cancel those out. I made the V2 disappear. But in order for this to still be equal, I have to do the same thing to both sides. So if I divide one side by V2, I have to divide the other side by V2. And that's how you rearrange an equation like this. So that's all kind of messy looking, so I'm going to rewrite it. P2 equals P1 V1 over V2. It is easy to transpose the numbers and the letters. So write it down and then double check. It's a shame to do all this work and get the wrong answer just because you switched to 1 and a 2. Now I'm just going to go over to my table and find these numbers. So here's P1, so that's 3 atmospheres. Write the units, always, always. V2 is 5 liters. and that's divided by V2, which is 2 liters. Then look at the units and cancel them out if there's any that cancel. So the liters cancel out. I'm left with a unit of atmospheres. I'm finding a pressure, and so that's good news because that's a pressure unit. I'm rummaging for my calculator. So I'm going to have 3 times 5 divided by 2. Should have done that in my head, but the calculator doesn't lie. So this equals 7.5 atmospheres. All of these numbers have 2 significant figures, and so my answer is going to have 2 significant figures. And then ask yourself, well, does this make sense? So we had a volume of 5 liters, and we squeezed it down to 2 liters. Do we expect the pressure to go up or down? We expect it to go up, and it did. Probably one of the more common mistakes that students make is they'll get something upside down, and so you'll end up with the pressure going in the other direction, and so then you can catch that at the end. Any questions? Yes?
Couldn't you just fill in the blanks with the original equation? Like, you know what P1 is, what V1 is, and V2 is. You can just be like V1 times V, or V1 times V1 is 15. V2 is 2. What times 2 equals 15?
You could. This is not the only way to do it. People have a lot of different ways of thinking about math. And so if you have a different method that works, absolutely go ahead and do it. I am addressing most of these examples to people who struggle with algebra.
Okay.
Yeah, because I have found that that's most of the students in a Chem 20 class. Just algebra is just kind of a mystery, and that's fine, you're in good company. But I can help you figure out the algebra that you need for chemistry. So if you have issues with algebra, please come and talk to me. Please ask questions, because I'll help you. Okay? Any other questions? I don't remember what's coming next. Oh, another law.